So just like we did for functional limits, right? For functional limits, we developed a way of showing when a limit doesn't exist by using sequences, right? We took two different sequences that both approached C, but whose limit under F were different, right? When that happened, we had a limit that failed to exist. Now, some of the details of this I'll leave to the text, but we do the same thing following the same logic with finding a method for showing when a function is discontinuous. So the idea is if a function is continuous, then its limit is f of c. So under that assumption, we have a sort of analogous sequential criterion for continuity, where if we have a sequence x sub n that approaches c, then f of x sub n has to approach f of c. So our job in showing a discontinuity is to produce a sequence that goes to c, but that doesn't go to f of c under f. So we need some sequence going to c, but f of xn not going to f of c. So as soon as we do that, we've shown that the function can't be continuous there. And our next example is going to be a variation of the Dirichlet example from the previous video, where now we're going to have, say, 0 if x is irrational and just x if x is rational. And remember, the way we graph a Dirichlet function is we think of kind of fuzzy lines, right? So this line y equals x would be what happens at every rational number, and then we would still get 0 here for every irrational number. And our job in this example is to show that the function is not continuous at 1. And the reason that's going to turn out to be the case is because no matter how close I get to 1, right, I jump up to x or back down to 0, up to x, back down to 0, it never settles down around the function value. All right, so we need to start by finding f of c, because that's the thing our sequence has to avoid. So f of c is f of 1. 1 is a rational number, and so f of 1 is going to equal 1. Right, now our job in this case is to figure out a sequence whose limit under f isn't equal to 1. And the way we're going to do that is to make sure that our sequence stays on the top piece of the function. So I want a sequence that's irrational, that converges to 1, but if I do that, then f of that sequence is going to stay at 0, because they will all be irrational numbers. So let's take x sub n equal to, say, 1 plus root 2 over n. That has to be irrational because root 2 is irrational and n and 1 are rational. Note that this goes to 1 because root 2 over n goes to 0. Right? So now let's look at what the function does to f of xn. Well, no matter which n I choose, if I plug an irrational number in for x, I get 0 out. And so I get 0 for all of them. That's a constant, so that limit is 0. And note that, let me write it this way, the limit of f of xn is equal to 0, but that's not the same as f of 1. Right? In order to be continuous, that limit would have to be f of c. C is 1 in this case, and f of 1 is 1. So I created a sequence I did it in such a way that it lives on the top part of my piecewise function, which means no matter what n is, the function evaluated there gives me 0 because I'm plugging in an irrational number. And so I've arranged for the limit of the sequence under f to be 0. That's not what I needed for continuity, and so continuity has to fail. So by the discontinuity criterion, f is not continuous at x equals 1. And again, if it were, then all sequences would have the same limit f of c under f. Well, sequences that approach c. One for you to try would be the sort of interesting property that there's actually exactly one point where this function is continuous. Now this is kind of an unusual circumstance, I think, for what we're used to in calculus, where we might have a function that's discontinuous at a point or two. But this function is actually discontinuous everywhere except one point, and that is the point x equals 0. So a good exercise would be to try to prove that the function really is continuous at x equals 0 using the definition. Some version of that will appear in subsequent problems.